In this video, I will talk about the forward propagation with Bystrom. The Bystrom has been added in the previous video, and I explained in detail what is the purpose of adding Bystrom in the network, in the neural network. So in this video, I'm just wanted to explain how we can move from input to the output when we have Bystrom added in the network. I already explained forward propagation without Bystrom, so this video will be a bit shorter than earlier one. So let me just talk about the weights. Remember that one thing we want to change from the previous videos, or maybe the only lecture number 11 it was, where we added the weights from every input to the neurons in the hidden layer. But the problem with that is we do not have always one hidden layer. So when we do not have one hidden layer, but we probably have, for example, 28 hidden layers with 52 neurons in each hidden layer, then writing a solution like this, W1 x1 plus W2 x2 plus Bystrom, become very simple. It is not feasible in other sense for in mathematics point of view. So what we do, we introduce a notation W, capital W, I will talk about that, and introduce one notation in the superscript 1. So this W1 will be a matrix. Then we have, for example, another calculation. Then we introduce 2, and the 2 means we have a hidden layer. Some people call that the weights are from 1 to hidden layer 1, hidden layer 1, then this is 1. From hidden layer 1 to the output, you have, for example, 2, then this is 2. That's how the superscript is read in the neural network. Okay, but the question was to write all the weights in the matrix form, since this is more suitable mathematical point of view. For example, without the matrix form, we have uh, one connection from input x1. X1 is a feature, and we call that the weight from input 1 to input 1 to hidden layer 1. 1 means input 1 to hidden layer 1 and neuron 1. If we have, for example, connection from x1 to the hidden layer and neuron number 2, then we have, for example, the weight. Then we have weight, the connection is 1, and input number 1, and this is neuron number 2. So we will write 2 over here. So we have 2 over here. That's how the introduction of this notation comes. So for example, for the third neuron, since this is the connection from input to the hidden layer 1, so we call it, in the superscript we have 1, and then we have, for example, input 1, And the third neuron, this is this is first neuron, this is second neuron, this is third neuron. So we write third neuron over here. So symbolically, this becomes 1, 3 in the subscript. And we do the same, all the calculations, for example, from X2 to neuron number 1, from X2 to neuron number 2, from X2 to neuron number 3. So we have, for example, how this will be written: W, hidden layer 1, and then we have, for example, 2, since the connection is from input number 2 and the neuron number 1. So this becomes W1, 2, 1, and so on. So I hope you get the idea. Similarly, if you talk about the output of this will be the input of the output, the final output of the network. Then we have W2, since this is, for example, 0, this is 1, this is 2. Notation and the indices depends on the book, or maybe in different people use different notation for that. You just need to understand what is the meaning of this 1. The meaning is the from input to the hidden layer 1, from the meaning of this 2 is the hidden layer 1 to the input, the final output of the network. So this is 2. Okay, so maybe I write it in neat form. So we have a connection from first neuron to the output, that will be W2. And what is the neuron number? We have, for example, 1. Okay, since there is only one output, so we don't need the second index in the subscript. Again, suppose from neuron number 2 to the output, since we are working in the second layer and it is the neuron number 2, so the neuron number 2, then the last one is W2, and we have 3. Okay, so this was all the weights we have. We want to write this, since this can be thousands of million of weights we had, so we call that W2 and we call that W1. Okay, not only this one, but the missed one, which I did not write over here. Okay, all will be written in the matrix form. The last thing is the bistrum. Since we added the bistrum, for bistrum, we have, for example, uh, the bias is from input 1 to neuron number 1. The bistrum will be added. Okay, you remember that, how we can add that. I will write the mathematics. So, and then we also have, for example, the bistrum for 1 and from input number 2. Okay, then we have the bistrum from 1 from for hidden layer 1 to the third, since this is the third neuron, this is third neuron. Similarly, we have, for example, the bistrum will be added in this calculation over here. Then we have, for example, the bias for the hidden layer to the output, that is 2, and we add over here is 1. Okay, B2 1. So there will be three biases, since there will be 3 calculations, 3 biases over here. Then you apply the activation function. Then here you have only one bias that will be added. Let me just write a mathematics of that. Suppose we have Z2, Z2 1 1. Then we have Z2 1 2. Then we have Z2 1 3. Okay, this is just a linear combination of all the multiplication of x1 and the weights, and also the x2 and the weights, right? I will write that over here. But remember that we did not apply the activation function over here. When we apply the activation function on this term, then we get, for example, A11, for example, 2, and so on. Okay, so we have, for example, Z2 1 1, that will be equal to x1 weight is from the input layer 1 1 plus x2, then we have weight from 1 for first from input to the hidden layer, we have 2 1 plus, then we have bias, that is the only term added over here, bias b1 1. For the second one, I can simply write Z2 1 2. Remember, we did not apply the activation function. That will be x1 1 2 plus x2 w1 2 2 plus b2 1. Then we have z2 1 3. Input 1 2 3. We have x1 w1 1 3 plus x2 w1 2 3 plus, then we have bias 1 and 3. So this was a calculation uh, for Z2 1 1. We calculate these values from these equations. Okay, so what we do, then we apply the activation function. So we apply the activation function to introduce the nonlinearity in the data. So fz211 will be equal to a2 a211. Then we have activation function applied to z212, and that will be equal to a212 f z213, and that is a213. Okay, so that's how we get the final value, final input. This is the final input. It means that this neuron will have a value of a211, and this neuron have a value of a212, so on. So similar to these inputs which acts as input for the hidden layer, these values a2 1 1 acts as an input for this output. Output is for the neural network. So what do we do? So Z3, here the value for Z3 will be equal to Z3 and Z3 with, there is no subscript 1 1 or 1 2, since there is only one output, that will be equal to Z3 Z3 A112 W12 plus A12 W to 2 plus A213 W to 3 plus B1 2. Okay, so we just added the bias term. As I repeated earlier that I already did this calculation in my previous video without the bias term, and we are just repeating the calculations for the bias term added in the equations. Now, how the activation function apply? Let me just talk about the which activation functions we are discussing in these lectures. Uh, the one activation function which is has a very good derivative easily you can easily find the derivative is the sigmoid activation function. So we have, for example, the final answer will be when you apply activation function on Z3, and we have 1 plus e raised to power minus Z3. So you put the number or vector, whatever the value is over here, and you get different answer. This is the final answer of our neural network. This is the value that we get from machine learning, right? So let me just talk about the back propagation, forward and back propagation. This was the forward propagation. Forward propagation means that we move from input to the output, and after reaching out at the output, we want to optimize the weights. We want to optimize the weights, so we move from uh, output to the input. This is called epoch. EPOCH. So you completed one epoch when you move from input to the output, then output to the input. And many epochs are required for good or maybe optimized weights. So how we do that? So let me just finish this lecture with back propagation as well. Back propagation. For back propagation, we need to use derivatives. So first I introduce y hat. Y hat is f of e. It means that we are actually using the previous notation. This e is our z2. Okay, maybe z2 and yes, z2 and z so on. So this will be some variable. Similarly, we want to make a derivative of this y hat with respect to e. Okay, that will be equal to f dash e. E is for example, we have, let me just for back propagation, let me just draw a network. It will take some time, but we need to understand the theory as well. Understanding is very important. Let me just talk about that. So for example, we have two inputs with XA and XB. And then we have, for example, one output. Very simple network. This is called perceptron in the theory. Then we have, for example, two weights, WA, and this is WB. Okay, the summation will be equal to E, XA WA plus XB WB plus and the bias term. Okay, so there is a bias term, capital B maybe, for this very simple perceptron. What we do, why we introduce perceptron, the reason is we want to understand the basic structure first. Then we extend that to all the other higher order neurons. For example, this is the very simple problem. Or maybe if we have, for example, this is a one perceptron, then this is another perceptron, this is third perceptron. So that's why we have all the knowledge from perceptron, and we extend that to the higher order neurons. Okay, then you apply, for example, f of e, activation function on e, and we get y hat. That's what we have over here. We take a derivative of y hat with respect to e, and e will be equal to xa xawa plus xbwb, and the Bystrom, which is b, partial e by partial wa will be equal to xa, partial e by partial wb will be equal to xb. And what is the new thing over here? We have to take the derivative of e with respect to the Bystrom as well, since we want to optimize the Bystrom as well. The j, the output, one is this value. This is the answer of the neural network. Suppose we have the correct answer, which is y. Then we want to find the error. So we take a difference of y with y hat. Then we have, for example, we define it like this. J will be equal to 1 by 2 y minus y hat, and this is square. We add this 1 by 2 since we need to take a derivative. When we take a derivative, this 2 will be come from the power by the power rule in the derivative. So that's why we have 1 by 2 over here. Now partial j by, since we want to optimize the error or reduce the error, so partial j by partial w1 will be equal to minus y hat partial w1 minus y hat. Since you have to reach the wa, and there is one variable in between e, so first you have to take a derivative of output with respect to e, then e with respect to a. So you have to apply the chain rule. So partial y hat by partial e by partial w1. Similarly, we have partial j by partial w2, not w2, but first you need to define the w first, minus y hat f dash e, since we already call this derivative as f dash e. So partial j by partial wa will be equal to, we call this as delta, and partial e by partial wa. W1 was a dummy variable. W1 contains the wa and wb. That's why we use the matrix form. So the answer is delta and xa. Similarly, partial j by partial wb, that will be equal to minus y hat partial y hat by partial wb, the second variable, since we want to optimize wa, all the weights. In this case, we had only wb. So we have minus y hat, partial y hat by partial e by partial wb. And similarly, when we define delta, we get delta xb. And the last thing is the derivative of j with respect to the Bystrom b. Since in this calculation, in the y hat, we have b involved as well in the calculation. You can see that there is a b. So we need to optimize this Bystrom as well. For that, we take a derivative. So partial j by partial b will be equal to minus y hat, and partial y hat by partial b, and partial, then we have, for example, z, partial e by, uh, that will be z. Okay, so here minus, probably we don't need z over here. We don't require z, right? Okay, minus y hat, partial y hat by partial e, and partial e by partial b. So delta will be equal to minus y hat f dash e, partial j by partial b, delta partial e by partial b, that is equal to delta. Okay. Finally, we already calculated all the derivatives. That's what is required in the neural network and also in the physics informed neural network. These are all the derivatives that we calculated. Now we have the final answer. The WA must be updated with the following equation. Remember that you must be not comfortable probably with these equations. We will talk about that by considering particular example, and we will talk about all these things in that particular example. Then you will understand that. Then you need this theory. So WA will be equal to minus alpha partial J by partial WA. Then we have WB. WB will be equal to minus alpha partial J by partial WB. And finally, the Bystrom will be updated as well. B minus alpha partial J by partial JB. So these are all the equation which will update the WA, WB, and B. The weights and the Bystrom all will be uh, updated. So you move, for example, here to here, then you come back, then you update the value again, then you move back to the output, then come back. So you complete many epochs so that you get the final answer by applying these equation again and again. Alpha is the learning rate. It is a kind of parameter which defines the number of epochs is required. If alpha is very small, for example, very small, then you need many epochs. If alpha is very large compared to 1, it is a bit larger than this, then you need less number of epochs, but the error probably will not be good enough. Okay, that's why you need a good computational power to solve a neural network. Thank you for watching.